is a home energy monitor, sometimes also called an in-home display. It basically talks to your smart meter and shows you what the current readings are, what energy you're using, that sort of thing. It does that by using the Zigbee protocol to read data from your smart meter. The device by itself doesn't record data or anything like that. It actually just pulls it all straight from your smart meter. So why did I choose this device to do a talk on at BSides? Turns out that the EMU-2 is one of only 2 devices that are approved by BC Hydro for people to use as a home area network device to connect to their smart meter. It also only costs $35, so it's pretty accessible if anyone wants to just get one of these. You do have to be a BC Hydro customer, I believe, before they'll sell you one, but otherwise it's pretty cost effective. And it's a fairly, I thought, representative device of what you kind of come across when you're looking at embedded systems and trying to consider their security. It communicates to your PC over USB, talks Zigbee, and just seemed like it'd be a fun target to look at. So I mentioned that it's one of 2 devices approved by BC Hydro, and I kind of was a little bit curious why that would be. So I looked it up, and BC Hydro's statement says, BC Hydro requires vendors to go through testing so that we can ensure their energy monitors are compatible with BC Hydro's metering system. Currently, Rainforest Automation is the only manufacturer with devices that have been validated to work with BC Hydro's meters. Oh, really? The Zigbee Alliance says, the Zigbee certified program ensures that products built using Zigbee function as expected and products from different manufacturers interoperate with each other. So one of them has to be lying? I don't know, I think we can probably all agree that the only thing worse than paying for a certification is paying for one twice. Shouts out to anyone who runs a certification program. The other device that is also approved is the Rainforest Automation Eagle. I got some of the specs on it here. It displays your real-time energy usage, similar to the EMU-2, but it lets you view it on a web browser. It runs an internal web server. It also can connect to Rainforest Automation's Energy View apps, and finally just send your data to the cloud. So I thought about looking at this one, and if you can't tell, there's a fish there. I thought maybe that'd be a little bit too easy. Just because this is BSides doesn't mean we have to make it that easy. So I'm sure it'll be a fun target if anyone else wants to look at it, but I wanted a little bit more of a challenge to go through. So back to the EMU-2. The first thing we want to do when we're testing a device, any device, this device, is look up what public information is already available and documented that might be useful to us from a security perspective. There's no sense in making anything more black box than you need to. So I was looking for things like, what technologies does this device use? Maybe how does it store any sort of sensitive data? What sensitive data will it have? Will it support firmware updates? Are firmware updates available? All that kind of things. And so what I found is that there's actually pretty decent documentation on this device. Specifically, there's a user manual and a quick start guide. Nothing really special in those though. There's also a technical manual that's available off their website, and it was actually really good. Actually had a lot of technical details instead of just claiming to be a technical manual. And finally, there's what they call the Raven XML API manual, which is the manual for the commands supported for the device's USB interface. So read through the technical manual, and it covered a lot of things that I'd already known or expected about the device. The device, communicates using Zigbee, supports the Smart Energy profile of Zigbee, talks about how to power on your device, that kind of thing. One thing that it did mention that was kind of interesting was this diagnostic mode. So you can get to the diagnostic mode according to the manual by pressing both buttons on the device at once, and which will put you into a configuration mode, and then if you press those buttons again and hold them down for 5 seconds, you get to the diagnostic mode. In the diagnostic mode, you can do a few different functions, one of which is a device hard reset, to basically tell the device to clear out every set of data and settings it currently has. One screen then would show you the device ID, the MAC address, that kind of thing. And then the last screen would show the device's link key. So when I first read this, I thought, hey, that could actually be really interesting. That might be something that's valuable or something that you don't want easily displayed. But it turns out it's not actually anything special. So when we go through the Zigbee section at the end of my presentation, I'll talk a little bit more about the link key and how that relates to the device pairing process. So the Raven XML API manual documents how you talk to the device over USB. Turns out that the device's USB port is basically just a USB to serial adapter. I think they require that you download the prolific drivers if your computer doesn't automatically find it, and then basically, according to the manual, you just connect to it like a regular COM port. 115 kilobits per second, stop bits and all that default. And I feel like I lost a slide. Oh no, it's coming up. And so then it says once you connect to that, you talk to the device using basically XML formed commands, and it'll respond with XML responses. So an example command from the manual is get device info, and the example response that it says you should expect to see is device info, including the device MAC address, the install code, and the link key and firmware version. So that sounded like it'd be interesting, so connected it up, tried it out, and it worked great. I immediately started seeing XML data scrolling by as the device was pulling data from the meter and displaying it on the screen. I could read data or send commands to it. So as soon as I had that working, the first thing that I immediately thought is, okay, well, they've documented what commands are you supposed to send to the device. How can we start abusing it instead? So normally you could send a command like give the device a nickname, call it test, but it's probably way more interesting to call it test 20 times. So I sent that command down to the device, and this was the response. Specifically note the nickname field and then the account field. So this can't be good. At this point, I decided, okay, there's clearly some input parsing issues, which I'm not surprised to see. That's not a good thing, but I should probably stop poking at it too hard, because if I'm overwriting from one field into the next on embedded devices, it's fairly likely that I'll just start overwriting into device memory and overwriting firmware, and I'm going to brick this device before I've even gotten started, and it's going to be a really lame BSides presentation. So I moved on to the next thing. The Rainforest automation to help people who don't want to pull up a serial console and type out XML commands manually. They provide some software called Personal Meter Reader, and it's basically free and lets you collect and visualize and see all the data coming from your home energy monitor. Maybe you want to, I don't know, analyze it on your computer. I'm not sure what the use case was, but it lets you pull down all that data. The software supports both the EMU-2 and the Rainforest Automation Raven, which is kind of like a USB dongle version of the EMU-2, a fairly similar device, and it communicates to either device over USB. So since it's talking to the device over USB, just like we were talking to it over the serial port, I basically assumed that it's using the exact same protocol, but vendor software often will have interesting features that you don't otherwise have access to. And as an example, this application says that it supports doing firmware updates to the EMU-2 device. Firmware updates are always an area of interest when you're looking at a device's security. But the first thing I wanted to start with was just looking for some hidden modes, hidden functionality that might be in the application. So I took a very quick look at it, and I discovered that the application was written in .NET. .NET, just like Java, is basically application reverse engineering on easy mode. So I don't actually have a ton to say about it, but it made the testing go really quickly. Opened the application using a tool called ILSpy, and basically decompiled the application, and I immediately spotted there's going to be a few interesting command line flags. So one is debug, and one is /trace. And so on the screen here, it's probably hard to see compared to my last slide, but normally the application looks like this. On the next one, we've got two more options in the top bar, one called show debug and one called diagnostics. Show debug is kind of pulled out to the right there, and basically it gives you some information about what's happening, lets you choose which commands to send to the device, see the responses, or put the application into a demo mode. And diagnostics mode lets you see all the raw commands that are being sent to the EMU-2 device, and see all the responses and log them to a file if you like. So since we already had the XML manual, a bunch of these commands we already knew about, interesting to see but not super useful. But then I noticed there's actually some commands being sent and received that I don't see in the XML manual. So the next thing I want to take a look at is, well, what commands does this application actually support? So I continued digging through it using ILSpy. ILSpy is basically just an open source .NET assembly browser and decompiler. It's based off of .NET Reflector, which is now a commercial closed source tool. But back when it used to be open source, you could just use it for free, and so the ILSpy project kind of continued that. As you can see in the screenshot here, it really is just like browsing the source code of the application. You get function names, variable names. The only thing you're really missing is comments from the source code, but it makes it very easy to quickly get a handle on what an application's doing, how it's parsing input, what functionality it has. So I started to look for how does it talk to the device, and how does that firmware update mechanism work? Basically, what undocumented API functions exist. My first rule of technology is basically that implementation never matches documentation, so I wanted to see what else we could find. It turns out there's 11 commands in the personal meter reader application that are used that aren't in the XML manual. So here's a list of them, and here's the rest of them. So in this list, some of it looked like just general commands, get some meter readings, kind of interesting but not super interesting. Image block and erase PDM, things like that, they look a lot more interesting. So I traced through it a little bit more and found that a lot of these commands, you not only need to send the command name to the device, but you need some additional options. But once again, since we can just more or less browse the application source code, it includes all those options in there as well. So here's an example of the image block dump command. So the image block dump command, I tried it out, and sure enough, it lets me read back what looks like the device's flash memory. And reading through the application, when you're doing a firmware update, after you do the update, it can then dump the firmware back, I guess, to verify that it wrote correctly. And so it says that sector 1 starts at 0, goes till that address, and sector 3 starts a little bit further down and continues on. So I considered just patching the application so that even though I'm not doing a firmware update, I could still do the firmware readback. But I figured it would be just as easy to make a quick Python script to do the same. So I got a script called serialdump.py, and I set it up to dump for me sectors 1 and 3. So I tried out the script, and it actually worked great. It's fairly slow because you have to send a fully formed XML command with a bunch of data, and then you only get back 64 bytes of data at a time. But sector 1 and 3 basically just didn't look like anything useful. It was just a bunch of zeros. Looking back at the application, the debug mode had a bunch of suggested commands, and this was one of them, and it said read at offset 40,000 instead. So I did that, and that actually returned some valid data. So I started reading around in that address range and was getting data in some parts and not others, so I decided let's just do this brute force way and tell it to read 10 megabytes of data out of this device and see what we get. And so sure enough, I hit some data. I'm gonna open this in WordPad for a really exciting demo here. Maybe. All right, so I got a file basically, it's on my screen, but screen extensions. Yeah, we're getting there. There we go. Maybe. Yeah. Comrade Alex told me that hardware security demos are always kind of lame, and reversing engineering demos are even worse. I cannot disprove that. I'm sorry. So here's basically what I pulled down from the device. It's clearly not just blank data, but there wasn't a ton of readable data. Eventually, as I went through it, I found some of, let's see, I found some of the settings we'd stored in the device, found test. That kind of thing. But I basically was wondering, okay, have I actually retrieved the device's full firmware? Started looking through it more, and it looks like I'd kind of retrieved some of the strings from the device, but a lot of the commands that I'd expect to see being parsed weren't there. Okay, back to the PowerPoint. Yes, all right. So at this point, I'd kind of explored the USB interface pretty completely. I'd explored the buttons that you could press and the menus you could get to. And it looked like there was some interesting functionality there. It looked like I might break the device if I poked too hard at the interface. So I decided it was time to move on to some hardware analysis. But a quick summary is basically that this device has pretty good documentation, which is always helpful. Parsing is going to be an issue, and the debug and undocumented functionality lets us read or write firmware if we want to do that. But clearly, we're not getting the full firmware, so we need to look more. So the next section I'm going to talk about is basically how to do some hardware analysis on a device. I'm going to try and cover it from the ground up and go into some detail, but there's a lot to cover. At the same time, looking at device hardware, interfacing to device hardware is actually a lot easier these days than it was even 5 years ago, and a lot of this stuff's actually quite accessible. So before you get a device and just start tearing apart its hardware, it's always good to keep in mind what you want your goals to be, what you're going to actually try and accomplish. Often it'll turn out that it's much easier just to look at device communications or device software instead of going straight to the hardware. So the things I was looking for is what kind of debug interfaces are going to be on the hardware. Can we actually get a full copy of the firmware? We tried through software, got some of it, but definitely not all of it. Can we get access to the device's stored memory? We're seeing, the nickname I gave to the meter and some other stuff, but I had a suspicion that I wasn't getting the full complete set of data that's stored on the device. And ultimately, you know, how can we take full control of this device? How can we get root, even though it doesn't run Unix? There's no root. Okay, so with any hardware security assessment, the first thing I always like to do is just once again look up what public information's out there. The FCC filings is probably the first and best source of information on a device if it talks wirelessly in any way. The link there take you right to the FCC lookup page. It says it's outdated and don't use it, but they can't stop me. You can also look up patent filings. Sometimes they have really good information. Most of the time, patents don't. They're actually pretty useless. Patents basically rarely match reality. Yeah, patents clearly are only ever filed for defensive purposes to build company shareholder value. Manufacturing documentation is also sometimes available. So similar to the technical manual or the XML manual, sometimes manufacturers of components of the device will put out a bunch of documentation, and then a company like Rainforest Automation might just then build that into their product, but the manufacturer's documentation is also going to be really helpful. And sometimes you can find information just off of a surprising variety of sources. So sometimes there'll be an engineer at the company who's got a super detailed LinkedIn page of all the technologies he used and all the challenges he faced and all the ways he solved them. Sometimes you can just Google for information about the device and someone's posted half its source code on GitHub. It's always worth seeing what's out there before you go to all the hassle of actually tapping into the hardware and trying a bunch of things that you might otherwise not need to. So I looked up the FCC filings. This is what you get basically when you go to the FCC page. I don't have a screenshot of it here, but I always like to do a search by the grantee code, which is basically tied to the company instead of the full ID. So the ID you see there, YCX RFA Z1052. You can just search for YCX, and that'll pull up all the FCC filings from Rainforest Automation. And oftentimes you'll find that they've got similar products that have useful information as well, or they've got some product they haven't brought to market yet, but they've registered with the FCC. And so the main things from the FCC filing that are going to be useful are the device's internal photos, external photos, sometimes the user manual if you're having a hard time finding that, frequency info if you're not already confident of what frequencies it talks on. Block diagrams and schematics are always useful, but you're only going to find those on old devices. So devices probably from about 2000 and earlier generally have those available. From that point onwards, all companies request that they be confidential, so you're not going to get access to them. Of that full set, the main thing I wanted to look for at this device was the internal photos, which are basically photographs of the internal circuit board and the components that are going to be inside the case of the device. If you're lucky, these photos will show the boards with enough detail that you can read the ID numbers off the microchips and ID them. If you're less lucky, you might just be able to see if there's programming headers or serial interfaces or that kind of thing. And if you're even less lucky, you'll probably just be able to guess that it's a fuzzy picture of a circuit board. It's hard to know what you're going to get. But for Rainforest Automation, they actually had pretty clear pictures. This is what you can see when you go to the FCC page. And they've even got pieces of their circuit board labeled, so you don't even have to guess. They got the trace antenna up the top, got some transmitter circuitry a little bit below it. Makes sense. So I moved on to then actually opening up the device. So this device was actually really strange. Normally, to open a device, the screws are hidden under the feet pads or something like that, under a sticker. This device, you actually have to tear the front cover screen off, and then under that, the screws are hidden. So that took a little bit before I figured that out. But it's actually relatively easy. The screen is just kind of glued on, it just peels off. Once you open it up, this is what you're going to see. This is my device. Basically, the circuit board, we've got the two wires at the bottom there just connected to the battery pack that you can hook up. And so once we see this, we don't actually have to fully reverse engineer the PCB here. Really all we're going to want to do is ID the chips that are on there and trace out how we can talk to them. And so before I go further, it's probably worth pointing out the connectors, the through-hole pins that you see in the middle there. When the device is fully assembled, they're actually accessible through the battery compartment in the back. So getting access to those, you don't even have to open the device up if you don't want to. They're just right there. On the back side or front side, I guess, depending how you look at it, of the device, the LCD is actually just soldered right on. So I thought about tearing that off, but since I'd looked at the FCC filings, I knew there was going to be nothing exciting under it anyways, so I just left it there. So next, I basically am gonna talk through what you want to look for on this board, and then I'm gonna give a quick summary of what each chip is. So when you're looking at a circuit board like this, you've got basically traces between the components. In this case, they're lighter green surrounded by darker green. You've got the external connectors on the left side there, the micro USB, no, mini USB, and the AC, DC, I guess, power adapter. Other than that, the only real connectors that you could solder a header into are in the middle there, and they're actually labeled. So that's the other thing you want to look at, is basically what are all the various labels on the circuit board. It says Smarter Technology and Rainforest Automation, so maybe we look up who Smarter Technology is. I did a quick Google, it just sounded like the same company, nothing too interesting there. The MAC address sticker there is kind of interesting. It looks like they just printed it off of a label maker, which kind of implies that they got a pretty limited production process. They're not doing a lot of this stuff automatically, but some guys actually printing off the label one by one. And then that's really it. Like, there's a lot of other things we could look at if we were trying to, clone this device or do other things, but we're just interested in what hardware's there, how do we talk to it. So going from left to right, the first chip is the prolific 2303HX, and so that is the USB to serial adapter chip. Basically, it connects to a USB port and outputs serial for you. Makes it really easy. It's a very common chip, doesn't really have any logic beyond doing that conversion. The next chip is the Winbond 25Q blah blah. It is a 1 megabyte flash memory chip, and so the way we know what each of these are is basically you take the chip markings, put them into Google, see what datasheet comes up. Almost always you'll get a hit as to what the device is, and usually it'll have a bunch of information about each device. So now we know that the device has 1 megabyte of flash memory. The next chip is an RF access, basically wireless modulation chip, and it says it's specifically designed to work with Zigbee communications to modulate the data you're sending out wirelessly, which makes sense because it's connected directly to the trace antenna on the circuit board. The next chip is probably the most important one on the board. It's the NXP or GENIC. Basically, GENIC made it. NXP bought GENIC. The JN5148. And so this is the main processor on the device. Looking up the data sheet for this, it's specifically designed to support Zigbee communications and a bunch of other functionality related to that. So I'm actually going to go through a few of the features. So the data sheet's public and covers all the useful information that you're going to want to know about the microcontroller. Some of the key points are that this is a single chip that integrates both the microcontroller running program logic as well as acts as a transceiver to send out the actual Zigbee packet data. Has a 32-bit RISC CPU, can run up to 32 megahertz, has 128 kilobytes of ROM and 128 kilobytes of RAM for bootloaded program code and data. It also has an AES security processor, which is going to need to do Zigbee, and supports JTAG for debugging. Finally, the last chip here is the TI-74L V08A. And I actually had a hard time finding a datasheet for this chip until I realized that it's actually just a TI clone of another chip. And despite looking big and interesting, it's actually just a dumb logic chip that does for and operations, depending on the input you give it. So it's not worth considering at all. So those are the chips. The next thing we want to know is how do we communicate to these? And we kind of know how we talk to the USB to serial chip, just over that USB port. The only other interesting one then is the JN5148 microcontroller. And so I looked up the pinouts on that controller and compared them to the connector interface in the middle here, and I found that the labels are actually completely correct. So the various pins you can test to see if they're wired to something by just using a multimeter and doing a continuity test, which basically sees if voltage can go from point A to point B on your probes. So if it's, you know, pin 5 on the chip, you put one probe on that and then put the next probe on the pin that you're wondering if it connects to, and if your thing says there's a connection, you can have a pretty good level of confidence that that's where it gets routed to. The labels in this case just made that a whole lot easier. So what we can see is on the right side, hopefully you can see it, I don't know. In the right side there's a number of pins, MISO, ground, SPI clock, MOSI, SSM, all of which are going to be used for SPI communications, SPI. And on the left side, there were some pins labeled IO 4, 5, 6, and 7. And so I looked up the data sheet, and basically IO pins 4, 5, 6, and 7 are either mapped to serial receive and transmit, or they're mapped to the JTAG debug interface. I read then a little bit further in the data sheet, and basically it says the reason they're mapped to both is you can either have serial output enabled or you have JTAG debugging enabled. You get one or the other, not both. All right, I think I need to go faster. So what are the tools that you need to do this? What are the tools that I use to do this? So if you got your company's budget to spend, or you just got money that's burning a hole in your pocket, you can buy probably, I guess, a bit more of a proper set of tools, but you don't necessarily need to do that. If you're just kind of interested in playing around with this, getting a start on it, there's always a lower cost option. So you're going to need a soldering iron one way or another, even if you don't want one. So if you're going to, you know, spend the company's budget, spend a few $100s, maybe $500 on a really nice soldering iron. If you want to do it yourself, just get a $25 one from Home Depot. I mean, that'll make your life a little bit more difficult, but it'll work. You're going to need a multimeter. You can spend $10 and buy one at Home Depot. That's what I got. Or you can actually get a proper one and buy a $500 fluke. The next thing that is going to be useful is a logic analyzer. It's basically like a way more limited oscilloscope, specifically for reading and accessing digital signals. You can spend $600 and buy a pretty nice one that connects to your computer. You can get standalone units. There's a bunch of options. On the other side of things, you can spend $13 and get a Saley Logic knockoff, or spend $30 and get a Logic Pirate, which is probably a lot more legit than buying a knockoff. Finally, the last thing you're going to want is a serial TTL cable. So normally when you connect to a serial port on a computer, back when computers had serial ports, they'd run at a higher voltage and signaling rate than serial TTL, which runs at a lower voltage. So you're going to need a different cable. FTDI makes a cable that does this. And I know people have been hating on FTDI lately, but I actually think it's pretty awesome that a company decided to go out and brick all their competitors' knockoff devices. I mean, people all complained about it, but it's like complaining about downloading Hot Tub Time Machine 2.avi.exe and then getting a virus. I mean, you wouldn't download a car. FTDI also makes a cable that can interface with SPI, JTAG, and a bunch of other protocols. They got two cables that basically look the exact same. They use the same microcontroller internally, but they've just got different pins on them broken out. So one version of it has the serial pins, one version has the JTAG, SPI, whatever other pins. I got both. You can get a ton of different JTAG programmers potentially though, so whatever's gonna work best for you. And the last thing that you usually need, I didn't need in this case, but usually you're gonna need a bench power supply to actually power the unit instead of just running it off of USB or however it's normally powered. There's a ton more tools that you can buy if you got budget to spend and you need them, but these are some of the basics that you're gonna wanna have. Okay, so software tools, I'll go quickly through this. You don't actually need to go too crazy when it comes to hardware analysis. There's a lot of open source tools that you might want to use. I like WordPad for data visualization. There's this program called Binary Editor BZ that, BZ, we're in Canada, that lets you visualize some of the hex output that a device might have. So that was kind of useful to me too. I don't actually know its history. It's made by some Japanese organization, but as far as I'm aware, Japanese only have cyber weapons for defensive purposes, so it's probably not going to be a virus. There's also something that you're going to need to interface to your logic analyzer. So there's a tool suite put out by SIGROC. You could also use the Saley logic analyzer if you've got that. There's a few options. And then last, for the FTDI cable, you're going to need to use libmpsse. So quick question, who knows what this is in hex? Show of hands. Hoping for more hands. You guys got to work on this. That's OXFF. So I mean, you could use a hex editor. You probably should use a hex editor, but sometimes WordPad's great. So connected up to the serial port. As you can see here, I did a fantastic job of soldering on jumper cables instead of a proper header. It worked pretty great. I was pretty happy with it. So I connected to the serial ports, wanted to see if they were actually JTAG as one of the options, but it turns out they're just serial. When you talk to the device over USB, it spits out the exact same things coming out this port. So sadly, we didn't have a JTAG interface to use there. The SPI bus, I hooked up my logic analyzer, intercepted the communications, had to play around with it a little bit, but otherwise it worked pretty good. At the bottom there, if you're using Saley logic, once you capture all your data, you can export it, and then you just got to transform it a bit. So there's a command there that I found pretty useful. But basically, I ran the device from boot to see if it would read all the flash memory and I could get access to the full device firmware. But what I've discovered is I got the exact same thing as when I read it out using my script over USB. It still looked like I was missing pieces of it or something was going on. So I decided the next thing to do is go back to seeing if we could just talk to the NXP chip directly instead of looking at the SPI communications. So the JN5148, according to the data sheet, has a bootloader, and with this bootloader you can then switch the chip into programming mode. And to do that, basically all you got to do is pull the MISO pin down to ground when the device boots up, and instead of booting, it'll drop into the bootloader. They have kind of a custom tool to do this, but all you really got to do is hold one pin on the other while the device boots, and it's good to go. So I ran their flash programming software, held down the pin, and was pleased to see that it actually worked. We can talk to the bootloader, their software. You might be able to see it, maybe not, but at the bottom it read back my device's MAC address, so I knew it was talking properly. But then I started to be concerned because under the flash field, it gets kind of cut off because their software is messed up, but it says device ID 13 brackets encrypted. So what does this encryption mean? I thought, you know, maybe it's lying. You know, who actually puts encryption on their device these days? No one. So I moved back to SPI again, and instead of just capturing the input, I thought let's read it directly. So I used the FTDI cable instead of a logic analyzer. Told it to read the first 3 megabytes, even though it's a 1 megabyte chip. But once again, exact same thing. Just repeated 3 times because I read 3 megabytes. So now I was starting to feel like maybe it really is encrypted, or maybe it's possibly compressed. I went back to reading more documentation and discovered that there's the application called the Genic Encryption tool, and it says you can use it to encrypt flash memory, and it's especially recommended for devices implementing Zigbee Smart Energy. So now I actually decided, you know, maybe it really is encrypted. So what are we going to do about this? Check the header for what we'd read back. Check the spec. It says, hey, you'll see a boot record. You'll see the MAC address. You'll see the IV. Sure enough, in our image dump, which you could probably read, had the magic value, had the MAC address on the top right, and then had the IV, which turns out to be _Rainforest _. I suspect that Rainforest Automation is one of those companies that thinks IV stands for invariant vector instead of initialization vector, but I guess it could be worse. Their stuff was still encrypted. And according to the docs, the encryption key is stored in an eFuse on the chip that you can't just read back directly, supposedly. So at this point, it seemed like the NXP software wasn't going to help me. It wasn't reading back anything useful. There's another programming tool called atomic programming that can apparently read more memory, but you got to buy their hardware. So I just searched on Google what else is available, and I came across this application called GenProg from the University of Karlsruhe. And usually using stuff off people's GitHub pages is not worth the effort, but this was just a Python script, so I thought I'd give it a try. Patched it to work in Windows, and dumped flash memory. But once again, flash memory still encrypted. So I decided, well, you know, the bootloader seems to be giving me some options, giving me some success. What other commands or functionalities there? The GenProg referenced the bootloader operations document, which I read through, and discovered that there's definitely some undocumented commands being available and used. But, you know, I mean, what about the ones that are just in this document? And so we've been reading from Flash the whole time, but there's actually the option to read from RAM instead. Looking at the GenProg application, it had that functionality built in. It just wasn't actually tied out to doing anything. Looking at the datasheet, it says when the bootloading program executes or starts up, it reads in flash memory and automatically decrypts it for the application to run. The user program doesn't need to handle any of this. So reading between the lines, it sounds like the bootloader reads in from flash memory, takes the encrypted image, pulls the key from eFuse, decrypts it, and it's got to go somewhere, so it decrypts it into RAM. So I made some updates to the GenProg script so that it could actually read from RAM, save it to a file, told it to read a megabyte of RAM, and I actually ended up with some new data. So that was exciting to see, but it was still just kind of junk data. I looked back at the data sheet, which are super useful, and it said, hey, you're actually supposed to read from RAM at OXF0000. So I tried that next, and I still just got junk data. But that was starting to make a lot more sense because the device needs to run the bootloader to get the program code stored into RAM before there's going to be anything interesting there. So I powered on the device and then pulled the MISO line low, so I dropped back into the bootloader after it had already booted up, and I had success. Instead of getting back the encrypted firmware image, I got back a completely different set of data. So this is where my BZ editor comes in to do some big data visualization. We've got like almost 1 billion bits here, so it's clearly some pretty big data. And as we can see in the top right corner, that clearly looks to me like a interrupt vector table. I don't know about you guys. But basically it turned out to be the full firmware image as well as all the stored data. I'd do a cool WordPad demo now, but I'm getting pretty behind on time. What did I find in this though? I found some interesting bonus commands. So we knew about the commands to read back the firmware. I found a few others that weren't documented, including getting some meter attributes, which didn't turn out to be too interesting. Erase halt, which sounded terrible, so I didn't run it. And this command called secret, which is still actually a secret to me. You send it, and the device just does nothing. But clearly it's doing something, otherwise it would tell me it's an invalid command. So it's an area for future research, I guess. Normally what we do at this point, now we've got the firmware image, is we try and reverse engineer it, decompile it, figure out what we could. The processor used in this device is somewhat obscure, so I don't think there's even going to be a processor module in IDA Pro for it. But it is just based on the open RISC architecture, so figuring out the opcodes and making your own disassembler probably wouldn't be too much effort, but I wanted to look at communications next, so that's what I moved on to. So the quick summary is basically the serial pins, they're mapped directly to USB, they're not too interesting, but the remainder of the pins that are accessible on the circuit board are mapped to SPI, which you can intercept data on, but it's going to be encrypted. You could read the flash chip directly, and it's going to be encrypted. Otherwise, you can go back to those serial pins and access the bootloader instead. If you try and read back flash, it's going to be encrypted, but if you read back RAM, it's not encrypted. You can get the full firmware image. So I'm going to try and go through Zigbee really fast, but I think that'll be okay. So Zigbee is a standard for low power mesh networking, runs on 2.4 gigahertz, just like Wi-Fi. It runs on top of a protocol called 802.15.4, which is kind of a spec for wireless devices that use low power. A lot of different other applications are written on top of it, not just Zigbee. There's 6LoWPAN, ISA 100, a few other ones. It's a protocol that really takes the OSI model to heart. It has layers, and then has more layers, and then has more layers. And it's got a few different iterations, so Zigbee isn't always Zigbee. There's like 20 versions of it. That's what it looks like. There's layers. The one thing you need to know about Zigbee is it's a lot like Bluetooth. There's application profiles. So similar to how Bluetooth has, hands-free, advanced audio distribution, a bunch of other ones. Zigbee will have a bunch of protocols or profiles that it supports, and I've got a list of some of them here. The one that we're going to be interested in is the Smart Energy profile. So Smart Energy is an application profile, and it defines a bunch of functions that your device can or should support, including price, demand response, metering, messaging, and so on. One of the ones that's going to be important to us is the key establishment cluster, and the over-there upgrade is just kind of fun, but we're not going to look into it. So what previous work has been done on Zigbee? There's actually been a lot of interest on Zigbee. Zigbee kind of hit the mainstream around 2009, I guess. So people started looking at it, started looking at the security of it, and various things were found. So a lot of weaknesses were found in certain Zigbee profiles. As an example, Zigbee Home Automation does key exchange by taking a fixed key, encrypting your new session key with that fixed key that's shared among every single device in the world, and ta-da, you've got your secure key exchange, except obviously, since everyone knows the fixed key in the world that everyone uses, it's not accomplishing anything. Eventually someone made a framework called Killer Bee, actually a few guys made it, and it's basically a collection of scripts as well as some firmware that you can load onto a device that let you analyze Zigbee communications in a bunch of different ways. So what tools are you going to need if you want to start talking Zigbee? There's actually a bunch of tools for doing Zigbee communications these days that are fairly low cost. There's the Atmel RZ USB stick, which is quite popular. Atmel has a little bit of a scam going where they program firmware onto this thing that's completely useless, so you need to buy a programmer from them to reprogram good firmware onto it. But the programmer is only $50 too if you get the Dragon, AVR Dragon. Otherwise, there's a bunch of commercial ready-to-go solutions. I listed a few of them here that'll all do a good job of being able to capture and potentially transmit data as well. I decided to go with the Atmel RZ USB stick because it works great with the Killer Bee framework. Although the Killer Bee firmware for it is actually kind of terrible, so you're going to want to use the Wireshark firmware that Atmel puts out instead, generally. So what does this let you do? You can load the Wireshark firmware on it and basically plug it into your computer, and Wireshark will now recognize it as a capture device, and you're capturing just like you're capturing off Ethernet. Wireshark turns out to actually have fantastic support for Zigbee decoding these days, so it's a really great way to start getting a handle on what's actually being sent out. So if that was all, that would be great, but probably not great from a security perspective. So even though we can capture data, all of the packets sent using Zigbee Smart Energy are going to be encrypted. And they're actually encrypted using two different encryption keys. One is the network key and one is the application link key. To get those keys from, say, your smart meter and your Rainforest automation device to each other, devices have an install code, and this install code is just printed on the back of it, usually printed on the back of a device, and that code basically maps to an encryption key. Part of the install code includes a checksum. The remainder of it you take, run it through a hashing algorithm, which is public, and you'll end up with the first encryption key used to start your key exchange process. And so the pairing process, this is straight from the manual. Basically, you send a join request, you join to the coordinator. It will then send you the network key that you're going to use, and it's going to encrypt it to your install code. You then take that key, send a new request and tell it that you want to talk to the key establishment cluster to perform the key exchange to get the final application key, so you've got all the keys needed. And I've got a diagram here that basically shows that a little bit more clearly. This diagram straight from the NXP documentation, actually. So what are these encryption keys actually used for? How does that technology work? Zigbee uses AES CCM star, that's like the actual name of it, to encrypt or authenticate packets. AES is obviously a symmetric cipher, CCM star is the block mode, and it's up to then each application profile and to some extent the devices themselves what encryption mode they implement. Zigbee Smart Energy uses mode 5, which means that packets will have the payload data encrypted, and there'll be a 32-bit message integrity check value also applied. So packets will basically be both encrypted and authenticated, which is exactly what you want to see for a wireless protocol. So if we want to do encryption or decryption of this traffic, the process basically involves calculating a nonce value, taking the encrypted data and taking the decryption key, running those all through the algorithm and getting the decrypted output. If you want to also then perform the MIC validation check, you're also going to need to have access to the packet headers because it covers the entire contents of the packet, so nothing can be spoofed. So the nonce calculation is basically pretty straightforward. It requires the source address of the device sending the packet, the frame counter value, which is in the header, and the security control flag, which is also in the header. The security control flag, you can't just take it straight from the header of the packet. I spent a bunch of time trying to figure out why nothing was working in my code, and it turns out the Zigbee spec at some point in time decided, hey, devices should no longer tell people what security mode they're using because that's giving away too much information, or I don't even know. It seems kind of crazy. But they decided, take that out, and instead the receiver or the transmitter should just know to, once they've received a packet, XOR it with the proper mode, which in this case is 5. So you need to take that, XOR it, and then you'll have the valid nonce. You won't have the valid nonce if you just leave that part out. So all of this actually sounded pretty complicated. Like I said, I spent a bunch of time trying to get it working. And is there just actually a library we can use to do this for us? And the answer is yes and no. Wireshark has fantastic Zigbee decoding, like I said, but Wireshark isn't exactly a tool for, generating packets and, doing all kinds of weird decryption checks and stuff. It's there to analyze network traffic. There's also a bunch of libraries available, but they're designed or put out by the companies that make the microcontrollers that talk Zigbee, so you can't run them on your computer. You could run them on the JN5148 or things like that, but not actually very accessible. So the next thing I looked at was the Killer Bee framework, since it has a lot of functions that are useful when you're trying to do Zigbee security analysis. The Killer Bee framework basically extends Scapy, which is protocol parsing and generation tool, I guess I'd call it. And that actually is really useful, but it also has some limitations. And basically, the Zigbee protocol supports a bunch of different ways to form and send a packet, and is actually quite complicated to cover all of those ways, which is why I was kind of impressed that Wireshark does such a good job. So the Killer Bee framework actually is only compatible with a few of those. The other like big downside, for me at least, is that it doesn't, that Scapy doesn't work in Windows, and Killer Bee is based on Scapy, and I don't know. Scapy's terrible for not working in Windows. Someone should tell them. So we could use the Killer Bee libraries, but they're going to need some patching. So I decided to think about what are my goals going to be when I'm doing this. So basically, I can intercept traffic, but I'd like to be able to decode and decrypt that traffic to see what's really being sent. To do that, I'm going to need the required encryption keys, the link key and application key, and finally, I'm going to need to, or I'm probably going to want to start generating traffic of my own, send it to my device, see how it processes it. So I'm going to need to build some of my own scripts and tools to do that. So I thought about some options, tried some things, decided the best thing that is probably going to work is to patch Killer Bee, even though it doesn't work on Windows. And then in doing so, I realized that a lot of the decryption functions in Killer Bee are actually just stolen straight from Wireshark. They made Python bindings for the Wireshark C library and just started using it that way, which I thought was actually a great idea. And so if I'm going to make some applications, I could do the same. And in the Killer Bee framework, there's a tool called Zigbee GoodFind, which follows a great idea and strategy, which is we're looking for encryption keys. We've got a memory dump. Let's take every possible value from the memory dump, try it as an encryption key, see if it works. The problem is that Zigbee GoodFind is designed to work against the 802.15.4 layer encryption. I said there's tons of layers. They also have their own types of decryption, and so that's not the type of decryption we need, so I needed to kind of take that functionality but make it for Zigbee Smart Energy. So looked into doing some Killer Bee patching. There's actually a library that already covers some of this. And as I started doing it, I realized, you know, my patches are just as bad as the stuff that's already there in Killer Bee. It works, but it's still pretty terrible. And I also discovered that it's actually really hard to get any reference data to use for this. No one has posted like Zigbee packet captures online that include any sort of useful encryption or decryption stuff. So it actually made it really tedious. I'm going to look at see if I can get my device to rotate its keys after this and see if I can post my Wireshark captures, because I think it'd be really helpful for anyone who's trying to explore this more. So one of the things I learned as I was going through the patching process is that Zigbee devices often leave out data fields. This, I guess, helps save space on the air. It's a low bandwidth protocol. So that makes sense. But what I discovered is that you're required to restore them before you continue processing. And so that's right. You got to take packet data that wasn't there, write it back into the packet, and then do your decryption, and then do your message validation calculation. Which I would think if you're validating your message, you want to validate the message you received, not some message you reconstructed. So I lost a few hours on that. But ultimately, I got to a script. I called it Zigbee Network Key Finder. Basically, like I said, takes your memory image, takes the data you're trying to decrypt. I patched it so it doesn't use Scapy. You just copy paste some values from Wireshark directly into it, so I could run on Windows. Made me happy, and I gave it a try. And boom, success. Took about 5 seconds to run, got right down to the bottom of memory, and told me that it had found the packet. Since we have the MIC validation check, we know for sure that it really is decrypting it, so there's no guessing. So I took that, put it in Wireshark, and it worked. But as soon as I decrypted that layer, the final layer was the application security layer, and it was still encrypted, as I expected, because you need 2 keys. So there's this whole process for doing the key exchange and derivation. There's certificates that get issued to each device, to kind of validate which device is which, tied to the device's MAC address. And it turns out that there's this company called Certicom. They're now owned by BlackBerry, I believe. And they somehow patented the technology that's used to do this encryption process, and also became the only CA for all Zigbee Smart Energy devices. So I guess they paid someone off to do that. I don't know. You'd kind of think that a Canadian company would be a little bit more honorable than to run a sham certificate selling business, but I don't know. Boo Certicom. But that all sounds pretty complicated. I'm running out of time. Like, what can we do here, right? What if that final key that gets exchanged after all that certificate process is just stored in memory? So I took all the data, put it back in my script, ran it, and success. Right at the start of memory, we've got that key. And so the interesting thing to note here is that these are symmetric keys. So this is really all I'm going to need. And I'm going to show this in Wireshark right at the end, but I'm just going to go through slides first. Basically, put it in, and we've got the network layer, it decrypts successfully, and we've got the application support layer, it decrypted successfully. So it's a symmetric key, which means that we can pretend to be the EMU-2 device to the smart meter, because that's the key. We could also pretend to be the smart meter to the EMU-2 device. So I pretty much hope that Itron Zigbee packet parsing is pretty solid, because BC Hydro, I think, is expecting that you can only ever talk to the device if you're an EMU-2 or a Rainforest Automation Eagle. But now that we have the decryption keys, we can send anything we want. I haven't done any testing against my smart meter. I'm not saying that you should, but that option is definitely available. Consult your lawyers or whatever. I'm just the technical guy. So in summary, Zigbee packets have a ton of layers. There's tools out there, but they're pretty scattered and can be hard to use. Zigbee Smart Energy in general does a pretty good job of key exchange and security. It's not like the home automation profile. It's actually a lot more solid. I didn't see any flaws in its techniques. But the thing to always remember is that if you've got an endpoint device that a customer has, chances are they're going to be able to pull those keys out. So with symmetric keys, you're never going to be able to know which side is which once someone has grabbed those keys. Signed certs aren't going to help you if you can just go direct to the keys. So I want to wrap things up because I definitely don't want to hold people up from lunch. But basically, in conclusion, we looked at this device from a bunch of different angles: software, hardware, communications. Debug modes were useful for pretty much all of those. Zigbee as a Zigbee Smart Energy as a protocol is pretty decent, even if it's pretty hard to work with. Pulling encryption keys from endpoint devices, in case you were wondering, is always pretty much completely possible. Electric utilities should not expect that just because they've said, hey, you can only use a Rainforest Automation device to talk to your smart meter, that that's actually going to be enforceable. So I don't know if we have any time for questions. I gotta know. But I'll be around. Come find me. Contact me anytime. Wes at Synac. Find me on the Twitters. And all the tools that I kind of showed here are going to be available at those links. Thank you.
Awesome. Sorry I had to cut you off.
I was going way ahead.
It's okay. I'm just going to make some announcements. Our lunch is served out there, and around 12:30 we're going to do another raffle for the pros and VIPs. Bit9's going to do a little bit